All right, welcome back. We're now on the fourth segment. I tried to make them a little shorter so you can take them in little chunks. We were talking about how we describe endothermic versus exothermic processes. And we were looking at how we would do this graphically. Now, to do this graphically, we would plot energy on our y-axis and some time or just reaction pathway. It's a very vague x-axis. We're just really using this to compare energy of reactants and products. So if we have an endothermic process, we have our reactant energy here, and the process requires energy, and so we would have to increase in energy to reach to the state of what our products were. So in this case, products are greater than our reactants. So if delta H is our reaction, it's energy of our products. It's always final minus initial, with one exception you're not going to see until AP chemistry with me. So delta H is products minus reactants. So if the energy of the products is greater than the energy of the reactants, we're going to have a positive delta H. And that's what we get for our endothermic process. Now, we can do the similar thing for exothermic. So we just graph our energy on our Y and reaction pathway on our X. But in this case, our reactants have a higher potential energy than our products do. So we have our reactants. When we break bonds, take the energy required to break bonds, compare that to the energy required to form bonds, we're going to see a release in energy as we go from reactants to our products. And there would be our products down here. Now in this case, delta H, which is still final minus initial, energy of products minus energy of reactants. And since products are less than our reactants, we're going to end up with a negative value for our enthalpy for this process. You need to familiarize yourselves with all of the ways: verbally, energy released and required; observationally, temperatures of the surrounding changing; symbolically, delta H positive, delta H negative; and in a reaction, heat as a reactant for endo. And for exo, remember, heat was a product. Should be familiar with all of the different ways we can communicate that in our processes. Now, we're going to start by calculating energy changes with phase changes. We're not going to be looking at breaking bonds as much as we are going to look at changes in intermolecular forces. Molecular forces, IMFs. Intermolecular forces are the changes we'll be looking at. Now, when we do these, we're going to be graphing temperature. So our temperature is on our y-axis, and heat, added heat, is on our x-axis. Sometimes you'll see time, and that's referencing how long you're adding a constant amount of heat. But really, it's the heat that's added that is what we're interested in there. Now, we can do 5 different things when we deal with a heating curve. So we'll start with a heating curve. We can heat a solid. So that would be our solid phase. We can melt a solid. We can heat a liquid. We can vaporize a liquid, and then we can heat a gas. So the maximum steps you will have on these types of problems are 5. So you can have anywhere from 1 to 5 steps in these problems for your heating curve or your cooling curve. So this is the solid phase. This is solid and liquid in here. This would be liquid. This would be the liquid end of your phase change. That would be your gas. So in between we have both liquid and gas. And then this would be your gas phase. And you know your phase transitions from other units. So I'd suggest you write these in. This is melting. This is vaporization, condensation, freezing. And you need to refresh your memory on those. I'm not going to spend the time to write them down. So you can pause the video right now if you'd like to write those down. Now, what we're interested in is looking at the heat involved here. So let's process our first one, and we would be looking at the change from wherever your starting point would be to the point of melting. Now, at this phase, not this phase, but during this transition, you have an increase in temperature. Therefore, we are increasing kinetic energy. Now, the next transition would be the melting process. And there's no temperature change there, so there's no changes in kinetic energy during this. What we're looking at here are changes in potential energy. So no change in temperature, no change in average kinetic energy during a phase change. So you can recognize a phase change by the fact that there's no temperature change, and we're looking at these flat portions of the heating curve. Now the next transformation or transition would be the heating of a liquid. Now since we have, during the heating of a liquid, an increase in temperature, we also would see an increase in your average kinetic energy during that process. So as we heat our liquid, the molecules in the liquid begin to move faster and faster and faster and faster until they reach the point where they can actually break the intermolecular forces. That requires energy to break your intermolecular forces and reach this phase transition. So this would be our phase transition. Again, there's no temperature change here. So if there's no change in temperature, there's no change in kinetic energy during this phase transition. Remember, your flat portions of the graph are your phase transitions. And then the last process would be heating your gas, increasing the kinetic energy of the gas. Increased temperature means increased kinetic energy. During a phase transition, we're not changing kinetic energy, we're looking at potential energy changes. Now, I want to erase this bottom just a minute to give us room to look at this. One final thing before we go on to actually doing these calculations is we'll be doing each step separately. So there's going to be up to 5 types of steps we'll be doing. There'll be 2 kinds of mathematics and 5 steps. 1, 2, 3, 4, 5. Maximum steps. It could be 1, could be up to 5. The total heat involved will be the sum of each of the steps. So we just add up however many steps were involved, and that will be our final total heat in Vimeo.